Hello guys, today we are going to see the different logic gates which are available in the digital electronics and how to make the Verilog code for this different type of logic gates. Basically in digital electronics there are three different type of logic gates. There are basic gates and universal gates and finally special gates. These three different type of logic gates are available in digital electronics. Out of three, in the basic gates we have three gates which are AND gate, OR gate and NOT gate. In universal we have two gates, NAND gate and NOR gate, and in the special gates we have two different type of gates, XOR and XNOR. Now let us see what are the truth tables and the logical expressions for the three different type of logic gates. We are starting with the basic gates. Let us start with AND gate. The expression for the AND gate is y is equal to a into b. That means the multiplication of the a and the b variables give the output of the AND gate. And the truth table for the AND gate are a, b and the y, 0 0 0 1 1 0 and the 1 1. And for the 0 0 the output will be 0, 0 1 the multiplication will be 0, and 1 into 0 0 and 1 into 1 1. This is the logic expression for the logic expression, and this is the truth table, and this is the boolean expression for the AND gate. And for the OR gate the expression is y is equal to a plus b. That means the addition of the a and b variables gives rise to the OR gate. And the truth table for the OR gate is 0 0, and I am taking the inputs 0 0 plus 1 1 1 plus 0 1 1 plus 1 1. And for the OR gate the symbol of the OR gate is this, and for the AND gate this is the symbol. Let us now see the NOT gate. NOT gate is nothing but it performs the inverter operation. That means if you have an input as 0, then the output will be 1. If the input is 1, the output will be 0. And the symbol for the NOT gate is, this is NOT gate symbol. And next we will go on the universal gates. In universal gates we have two type of gates. One is the NAND gate and the other is the NOR gate. The NAND gate expression is the y is equal to a into b bar. That means the multiplication of the a into b and the complement of the result gives rise to the NAND gate. Now it is nothing but we are applying the complement to the AND gate. Now the truth table for this NAND gate is, we are taking the inputs 0 0 0 1 1 0 and the 1 1, and this is the, for suppose I am taking the AND and the NAND gate. For AND gate the output will be 0 into 0 0 0 into 1 0 1 into 0 0 1 into 1 1, and as I say that the NAND gate is nothing but the applying the complement to the AND gate. That means the 0 will become 1 1 and the 1, then this is 0, and this is the truth table for the NAND gate. And now let us see the NOR gate. And the symbol for the NAND gate is same as the AND gate. We are giving the two inputs a comma b, and the output we will apply a complement. This is the NAND gate symbol. Now let us see the NOR gate. NOR gate is nothing but the addition of the a and b variables and applying the complement. It is nothing but applying a complement to the OR gate. And the truth table for this NOR gate is, and first we will see the OR gate, and then we apply the complement to the output 0 plus 0 0 0 plus 1 1 1 plus 0 1 1 plus 1 1. Now if we apply the complement to this OR gate, the output will be 1 0 0 and the 0. This is the truth table for the NOR gate. And And in the special gates, there are two type of gates. One is the XOR. The expression for the XOR gate is y is equal to AB bar plus A bar B. Now let us construct the truth table for this XOR gate. Same as in the previous for the logic gates. I am taking the inputs as A comma B and the output will be Y, and the 0 0 0 1 1 0 1 1. For the XOR gate, if the two inputs are same, the output will be 0. These are the same inputs, same, and these are different. Here 0 comma 1, which are different inputs, so the output will be 1. 1 0, different outputs, so output will be 1, and these inputs are the same, so the output will be 0. This is the truth table for the XOR gate, and the logic symbol for this truth gate is, this is the XOR gate symbol. Two inputs A comma B and the output is Y. And next and finally special gates are XNOR gate. XNOR is nothing but it is a complement to the XOR gate. That means if the inputs are same, the output will be 1, and the inputs are different, the output will be 0. And these are the same input, these are different, different logics, and this is the same input. And the symbol for the XNOR gate is A, B, and the output is Y. This is the truth table for the XNOR gate. So we have three type of gates: basic gate, universal gate, and the special gates. Out of these, we have discussed all these 9 gates, and 7 gates. And this is the AND gate, OR gate, and the NOT gate. These are the different truth table for the different logic gates. And let us make the code for these logic gates in the Verilog. In Verilog, there are 3 different type of modelings. One is gate or structural level modeling. Next one is data flow modeling. And finally, behavioral modeling. By using 3 different type of modelings, we can create the Verilog code for the logic gates. Today we will make the Verilog code for this logic gates by using this gates or structural level modeling. And okay, today we are going to make the Verilog code for the different logic gates. As I say that there are 3 different type of logic gates. One is the basic gate, universal gate, and the special gates. And we will make the Verilog code for these logic gates using the gate level approach. And to making the Verilog code for 3 logic gates, we can use the different platforms like EDA Playground, Cadence, Xilinx, Vivado. And out of these, I am using the EDA Playground. So let us start the Verilog code. For that, I am declaring a module with the name called logic gates, and I am taking the inputs A comma B and output and for AND, or for the OR gate, not for the NOT gate, NAND for the NAND gate, not for the NOT gate, and XOR, and last XNOR. These are the inputs and the outputs we required for our Verilog code. And let us assign the operation for each output. For the AND gate, the syntax is the AND. Assigning is I'm considering this as a G1 gate, and the output is the AND. And this output will be obtained by using the variable A comma B. Next, for the OR gate, OR is the syntax, G2 is the second gate, and the output is OR, and A comma B are the inputs. And for the not is the G3 gate. I mean, considering it is a G3 gate, and the output is the not. And I'm taking an input as we can wish. We have two inputs. I'm taking as A. You can also take B. And for the NAND Z4, NAND is the output, and the A comma B are the inputs. For the NOR Z5, I'm mentioning the gate. Sorry, NOR is the output. A comma B. And for XOR G6, sorry, A comma B. And finally XNOR A comma B. Uh, Here we obtain all the seven gates, and or not or the basic gates, NAND and NOR are the universal gates, and finally XOR and XNOR are the universal gates. Here we have assigned all the seven outputs. Now let us end the module, and this is the design code, and we have to write the test bench code also to run this operation. So for that, I am declaring the module with the name called tb, this is the test bench, and in the test bench the inputs will be considered as a register register a comma b, and output will be considered with the wire and or not and not XOR XNOR. And logic gates Hmm. Here I'm taking all the variables, all the inputs and the outputs. Now let us start. I'm by giving the initial begin command. Here I'm using some syntax called dumpfire, which is which will be used to obtain the graph. I will be show at the output time. I'm saving the file as a file VCD. You can save with your own name, and that's one. Okay. Now I give some inputs for A is equal to 0, B equal to 0, and hash 5. I mean, it is a delay, and A equal to 1. Sorry, A equal to 0, B equal to 1, hash 5, A equal to 1. I'm giving just some inputs. For every 5 delay seconds, the inputs will be changed for the logic gates. And I give all the sequences, and I'm giving the end. This end is for the this one, and finally end module. Okay, this is the design code for our logic gates, and this is the test bench code for our logic gates. Let us stimulate and show and see these gates are working or not. For this I'm taking to in the tools and simulators, I'm considering a IQRS Verilog 0.9.7, and I'm selecting the open EP wave. After run, we can see the outputs for this logic gate for the different outputs. I'm saving this the code. See, and I'm going to run this as we have to give some name. I'm giving the logic gates for this file, and see. And here we use the dollar finish to terminate the session. I mean, to terminate the inputs for the sequence. And after that, I am running this code. And after running, if we have no errors, we will obtain this like as a file. And here we can see that here A and B are the inputs, and these are the outputs. Here, here you can see that the outputs are initially A equal to 0, B equal to 0, and the AND gate is 0, and for the OR it is also 0, and the XNOR, in the XNOR we can say that the if the two inputs are same, the output logic will be high, and the output is also high. As we mentioned in the, as how the truth tables are there, the output is also like this. So these are the different type of logic gates by Verilog code for the logic gates using the gate level modeling. In the next video, we will see the Verilog code for the logic gates using the behavioral modeling. And thank you for seeing this video.